So as an introduction to our section here on solution concentration, I just want to remind everyone of the definitions of solute, solvent, and solution. So your solute is always going to be your minority component. So things that are present in the solution in smaller amounts. And actually, I should say minority components, because you can have more than one solute. The solvent is typically thought of as a thing doing the dissolving, but at the end of the day, you can identify it because that's the majority component. It has either the most volume or the highest mass. The solution, and this is how I abbreviate it, I do SOL''N. The solution is both the solute and the solvent. It's everything. Alrighty, so I just want to take a second and go over some of the new formulas here and talk about what they're used for. So the first one is weight by volume percent. It depends on the age of the textbook. More commonly nowadays, I see it as mass by volume percent. And so either way, if you're asked to do mass by volume or weight by volume, you're going to take the mass of your solute and divide it by the volume of your solution. Even though these units don't cancel perfectly or at all, the units on your final answer will only be percent. And you're going to multiply by 100% to get that. The weight by volume is interesting. It has a lot of historical significance. So in the 1600s, they started testing the quality of alcohol to make sure it wasn't watered down and whatnot by pouring it on gunpowder and igniting it. So typically, you would need 50% weight by volume ethanol in order to see ignition of the gunpowder. At that point, someone proved that the alcohol was legit. That's where they get the word proof from. And they weren't doing this kind of calculation, so instead 50%, which was the cutoff for ignition, became known as 100 proof. So if you're drinking and, well, after the semester's over, but if you look at some alcohol, right, and you're thinking about what does that proof mean, you can take your proof and divide by 2, and you're going to get mass by volume or weight by volume percent of alcohol in that solution. Moving on. So we also have mass by mass, which is super common. And in this one, I like this one a little bit better because the grams do cancel. And then we're able to justify why do we only have percent in our final answer. The other part that I wanted to add to the mass by mass percent is this idea of parts per million, parts per trillion. Super common and super important for people doing any kind of water chemistry. So if you wind up using your background to test water quality or atmospheric chemistry, whenever there's any kind of pollution, thank goodness, a lot of times we're still at the level of ppm or ppb. So because there's such small amounts of some toxic contaminants in our water, if we were to just do like a mass by mass percent, we would have like something with scientific notation, and that would be hard for the public to interpret. So instead of just multiplying by 100%, if we're doing parts per million, it's the same setup, but we multiply by 1 million. And that gets us to a nice number, like 4.6 parts per million. And parts per billion, ppb, is just as common. You would multiply by 1 times 10 to the 9 if you're asked to calculate ppb. So another type of calculation that we're going to be working on is known as molality. It has units of lowercase m, most played out letter in chemistry, right? So this little m It has to be lowercase. And a lot of times you'll see it with, it's kind of italicized, and that helps a little bit. Why invent another concentration unit? I mean, we already have molarity, and that works just fine. So the issue becomes if we're studying a solution or a system over a dramatic temperature change. Molarity with the capital M is moles per liter. But volume changes when temperature changes, right? If I start heating up some water, then those molecules of water are going to escape, and we're going to get higher and higher volume. The gas will start expanding. So density and molarity are temperature dependent. And so that's part of the problem with molarity. And we don't worry too much under normal conditions, right? Typically, we're at room temperature plus or minus a degree Celsius, so it's not going to affect anything too much. However, in certain types of problems, the problems we're going to get to later in this packet, since the temperature changes so dramatically, we're going to use molality. Instead of liters in the denominator, we have the mass of the solvent, and that has to be in kilograms. That part is really important. Just like here, it has to be in liters. Here, we have to be in kilograms. But mass is temperature independent. So 1 gram is going to be 1 gram regardless of the fact that you're at 0 degrees Celsius or 100 degrees Celsius. So that's the big draw here. The other new one that we're going to see a little bit here, but primarily in the gas laws section that we're going to hit upon really quickly, is mole fraction. So the subscript tells you what moles need to go in the numerator. And then in the denominator, you just add up all the moles. Moles should cancel with moles, so you're looking at a unitless quantity at the end of the day. If you have a 2-component system, like a solute and a solvent, well, when you add up their mole fractions, they should equal 1. And we can keep on extending that. 3 components, you add up the mole fraction of each of the 3 components, and altogether they should equal 1. Again, a super handy value to use, especially with our gas law material. So in this first problem, we're given some information about how the solution is prepared. It's reasonable enough information. I mean, we can imagine massing our sucrose in the lab. And separately, we would also mass the water. We can get the volume of the water, no problem. So just by collecting some data in the lab, we can then calculate molarity, molality, the mole fraction of the sucrose, and the mole fraction of the water. Let's start with molarity, which is the one we're most familiar with. So molarity is going to be the moles of our solute, in this case the sucrose, divided by the volume of the solution, so everything. I need to calculate the moles of sucrose. So I'm going to do 50.4 grams, and we know that 1 mole has a molar mass of 342 grams. That was given to us, but we just need a periodic table. Here we're going to get 0.147368421 moles of sucrose. I'm trying not to round until I'm completely done with the problem here. So that's going to go in the numerator. And in the denominator, I'm going to put my 355 milliliters, but I'm going to change it to liters. So I'm just going to divide by 1,000. So 0.355 liters. At the end of the day, after considering the fact that I only have 3 sig figs, I would report my molarity as 0.1 0.415 molar. And then you always want to put the identity of the solute. So it's going to be 0.415 molar sucrose solution. Probably I'd put AQ on this too, just to let people know that the solvent is water. There's so many solvents out there, especially when you get to organic, you're going to see many different solvents. All right, next one, part B, is something new. So in part B, we're asked to calculate molality. So the formula for that is going to be moles of solute. So we're good to go on that. The solute was our sucrose. We already have that value. Divided by kilograms of solvent, which this definitely sounds like lab data. They were able to measure that directly. So I have everything I need. It's just a matter of putting the numbers in the right places. So I'll start with the moles, which we calculated for the previous problem. 368421. And then I'm going to divide by 0.332 kilograms of water, since my water is my solvent here. When I did that and considered the 3 sig figs, I got an answer of 0.444 molal. So it's a 0.444 molal solution, and I can put the substance as well. You know, if I'm making a label or whatnot, you definitely want to know what's in that bottle or beaker. So in part C, we're asked to calculate the mole fraction with respect to that sucrose. So that means that the moles of sucrose would be in the numerator. And then we're always going to divide by total moles when we set up mole fractions. So we did calculate the moles of sucrose earlier, so I'm going to grab that number, the 0.147368421 moles. We've never calculated the moles of water, and that needs to be done because that value needs to be part of the total moles here. So I'm going to grab the fact that we have 0.332 kilograms of water and turn it into grams. And then I want to get rid of the grams and turn that into moles. So quite a bit of water, right? Makes sense though. We have 18.42397 moles of water. So now that I got that value, I can use it in the denominator here. So I'm going to do 0.147368421 plus 18.42397. And this, we're adding moles to moles. So it has units of moles. And what we need to know or think about with mole fraction, I'm going to erase that so it makes a little bit more sense to us. It's unitless at the end of the day. So moles will cancel with moles. And just like kind of like our percentages, the only unit on a percentage is the percent. And on the mole fraction, it's completely unitless. The units should cancel out. For that one, I got a very small number, 0.00794. So this is how, again with the 3 sig figs, but that's how I'd report my answer on a test or whatnot. Letter D is asking us for the mole fraction of water. There's only 2 things in the system. So we know that the X of water plus the mole fraction or X of the sucrose has to equal 1. And that's an exact 1. Don't let that impact your sig figs. You can put as many decimals as need be on that 1. So just subtracting, so I could do 1 minus 0.00794. And when I did that earlier, I got a mole fraction for water of 0.992. So that's one way that you can do it, especially with the binary systems or even a system with 3 things. If you know 2 of them, you can do 1 minus the 2 that you know to get that 3rd mole fraction. However, I did want to verify my work and set it up more formally. So I would do the mole fraction of water equals, and then moles of water have to go on top. So 18.42397 moles on top. And then we're dividing by total moles. So the same denominator would come out in both parts C and D. So 0.147368421 plus 18.42397 moles. Moles is canceling with moles. And that was a good check for me because when I did it, I got the same exact value. There you go. Alrighty, so on this molality problem, we have several steps that we need to take care of before we can actually plug numbers into the molality equation. So first thing is we need the moles of our solute, the potassium bromide. Right now we're in milligrams. So I'll change the milligrams to grams. And then I'm going to use the molar mass. So 119.0023 grams of potassium bromide. That's the molar mass. I just got it from the periodic table. And then that's going to be per 1 mole of potassium bromide. Always still check how units are canceling, right? No, you feel like you've been in chemistry forever now, but we still need to check our work. And so then we're just left with moles of potassium bromide. Pretty small number there. I got 1.134431856 times 10 to the negative 6 moles. Again, I'm going to try to hold that whole number in my calculator so that I'm not rounding before I get to the end. We also need kilograms of water. We were given the volume of water. We're also told to assume that the density is 1 gram per centimeters cubed. But 1 gram per 1 cubic centimeter is the same as 1 gram per 1 mil. So I can start with 5.00 mils of water. And I know that I have 1 gram per 1 mil. It's written with 1 sig fig, but it probably should have been written with a couple more sig figs. So let's just go with 3 sig figs. They probably should have given us a couple more, but by no means is that an exact number. We need this in kilograms though. So I'm going to do 1,000 grams in 1 kilogram. And then milliliters cancels milliliters, grams with grams. And at this point, we're left with 5.00 times 10 to the negative 3rd kilograms. So to finish up this problem, now I'm ready to plug it into the molality equation. So I'm going to do little m equals that 1.134431856 times 10 to the negative 6 moles of the potassium bromide divided by 5.00 times 10 to the negative third kilograms of our solvent, the water. So at 2.27 times 10 to the negative fourth molal. And again, I'd probably, if this was a label, I'd be as specific as possible so people know what they're dealing with. So what you're going to notice as we're working through these problems is that every single problem is a little bit different. We're going to have to use a slightly different approach depending on what they give us and what they're asking for. On this one, on part A, we're asked to calculate the mass percent ethanol. Honestly, I need to write a better problem. I don't know how to interpret that. I should have been more specific in what I was asking for. There's two mass percents. There's mass by volume percent and there's mass by mass percent. So just for practice sake, we're going to go through both. Let's start with mass by volume. So for that, we're going to need the mass of our solute, the mass of ethanol. We have volume and we have density, so we can use both of those to solve for the mass. So I'm going to do 10.0 milliliters of my ethanol, and it has a density of 0.789 grams per 1 mil. So we have 7.89 grams, because mils would cancel with mils, of solute of ethanol. Mass by volume percent will be the grams of your solute divided by milliliters of solution. And then because it's a percent, we need to multiply by 100. So not too bad because we just had the grams of ethanol. And we were given the volume of the solution. It's 100 mils. I know the units don't cancel, but the only units at the end of the day when you're reporting your answer will be percent. So 7.89. And if you're doing this type of calculation, I would include as part of my unit M over V percent, just so the reader or whoever's looking at that number knows how you calculated it, right? It's going to be slightly different than the mass by mass percent. So in order to calculate that, we need to know the mass of our solution. And we're given a density of that solution, so it'll be very similar to what we just did. I'm going to start with the 100 mils. And then our solution has a density of 0.982 grams per 1 milliliter. So we have 98.2 grams of solution. And so to do the mass by mass percent, if we're asked for that, I'm going to do the grams of solute all over the grams of the solution times 100%. So my mass by mass percent will equal, I'll grab the 7.89 grams of ethanol and I'm going to divide it by the 98.2 grams that we just calculated from the density of the solution. And when I went ahead and did that, I got 8.03% but I'm going to also indicate that that was a mass by mass percent. Alrighty, so in part B, we're asked to calculate the molarity of the solution. So definitely a calculation that we're familiar with. We're going to need the moles of the ethanol for the numerator. So I'm going to grab the 7.89 grams of ethanol that we calculated earlier using the density. And that along with the molar mass of ethanol, so 46.08 grams, grams will cancel grams, and I wind up with 0.1712239,583 moles of ethanol. You shouldn't round until the very end of the problem or worry about sig figs till the end. Just keep that number in your calculator. I know it's a pain to write these long numbers. That goes in the numerator, and then we need to divide by the liters of solution. We're given the fact that we have 100 milliliters of solution, so I'll just divide by 0.1000 liters. At the end of the day, we have a 1.71 molar aqueous ethanol solution. So in part C, we're asked to calculate the molality of the solution. I wrote down the moles of ethanol that we calculated in the previous segment. We're definitely going to need that in our molality calculation. That goes in the numerator. In the denominator, we're going to need to put the kilograms of solvent. That's where it gets a little bit tricky, and we got to be a little bit creative. So we can use the law of conservation of mass to estimate the grams of solvent. The thing that you have to avoid at all costs, though, is adding or subtracting volumes. When you combine different solutions, you can't assume, like if you have 100 milliliters of ethanol and you add 100 milliliters of water, that doesn't mean you're going to have 200 milliliters of solution. More likely, since the two substances get along, that they have like properties, you're actually going to have less than 200 milliliters of solution. So volumes cannot be added or subtracted just to find like a final volume or a total volume. However, you can get away with doing that with mass. So that's what we're going to do here. We're going to use this relationship. We could say the grams of solutes plus the grams of solvent will equal the grams of solution. So 7.89 here. I don't know what's going on with my solvent. We could just put it in as a variable or however you want to represent that. I do know, however, that I have 98.2 grams of solution. So I'm going to do 98.2 minus 7.89. And that way I know that I have 90.31 grams of solvent. I'm going to have to divide that by 1,000 because we need kilograms of solvent, right? So after I did that, I got 9.031 times 10 to the negative 2 kilograms of solvent. Now I'm ready to crunch my molality. I'm going to put 0.1712239,583 moles of ethanol in the numerator, and then I'm going to divide by 9.031 times 10 to the negative 2 kilograms. And when I did that, I got 1.895958 And there's only 3 sig figs, so at the end of the day, I would bump up the 9 to 90, and I would say I have 1.90 molal of the aqueous ethanol. So solution concentration is intensive. It is completely independent of how much you have. Think about it. 6 molar hydrochloric acid is 6 molar, whether you're dealing with 1 milliliter, 10 milliliters, 200 liters. It's going to have the same concentration regardless of the quantity. So because of this, in these problems where they're a little bit more vague, where they don't tell me how much I have, well, I can assume any amount that I want. Here, since it's 571.6 grams per liter, I'm going to make the math easy on myself, and I'm going to assume that I have exactly 1 liter of the solution. Because of that assumption, now I know that I have 571.6 grams of sulfuric acid. But if you're like, I don't like that, I don't want to assume 1 liter, I want to assume a different amount, that's fine, because you basically have a conversion factor here. So there's 571.6 grams of sulfuric acid in 1 liter of the solution. So assume whatever amount you want, and then use the conversion factor to extract the grams of sulfuric acid that'll be in the amount that you're using. At the end of the day, we're going to get the same answers though. So first is mass by mass percent. Halfway there, because I already have the mass of the sulfuric acid, and we're assuming a liter of the solution, and we know the density of the solution. So I'm going to use those numbers. I'm going to say, well, I have 1.00 liters, and I know 1 liter has 1,000 mils. And even though this is written as grams per centimeters cubed, I know in the back of my head that that's also grams per milliliter. So there's 1.329 grams of the solution for every 1 milliliter of the solution. So 1 times 1,000 times 1.329. So we wind up with 1.329 times 10 to the 3rd grams. So now we're ready to calculate the mass by mass percent, right? Because we're going to do the mass of our solute, the sulfuric acid, divided by the mass of the solution. And then the grams will cancel the grams, and it's a percent. So I need to multiply by 100. And I got 43.01 mass by mass percent for that first one. So I don't have enough board space. So just like I did with the previous problem, I'm going to add all of the important values that we calculated in red over here. So we already calculated the grams of solution, and we're probably going to need that for a future calculation. In part B, we're asked to calculate the mole fraction. The problem wasn't specific to what mole fraction, so I'm going to add it in. Let's calculate the mole fraction of sulfuric acid. We already know the moles of sulfuric acid, or we can calculate the moles of sulfuric acid from the grams of sulfuric acid. Let's do that actually. And that's going to go in our numerator once we get that answer. So using the molar mass of sulfuric acid, I was able to determine that we have 5.827301458 moles of sulfuric acid. That's a good start. Now, another thing I don't like about this problem is it doesn't tell us what solvent they used. However, typically, and I would say to the extent of 99.9% of the time, sulfuric acid is going to be made up or brought up in an aqueous solution. So your solvent with sulfuric acid is going to be water. That's how it's done. So let's make another assumption here. Assume that our solvent is water. They really should have told us that, but again, since it's sulfuric acid, it's safe to assume that it was brought up in water. Then I'm going to have to use that little trick that we've been using previously. So if we know the grams of solute and the grams of solution, we can solve for the grams of solvent because we have this relationship. Grams of sulfuric acid plus the grams of the water has to equal the grams of the solution. Mass is additive, volume is not. So I'll plug and chug here. So I got 571.6 grams of sulfuric acid, an unknown amount of water for now, and 1.329 times 10 to the third grams of solution. When I subtract, I'm able to figure out that I have 757.4 grams of water. So I did 1.329 times 10 to the third minus 571.6 to get this value. It's a mole fraction problem, so I'm going to take it one step further and convert this into moles of water. When I do that, I get quite a large number, but that makes sense. It is the solvent. So 42.03107.658 moles of water. And now for my mole fraction, I'm going to do the moles of my solute, or the moles of whatever they indicate here, right? So we're doing the solute here, the sulfuric acid, divided by the total moles. So I'm just copying down this number incorrectly, right? 5.827301,458. That's my sulfuric acid. That number is going to come out again in the denominator, as well as the 42.03107,658. That has units of moles. So both moles would disappear. And then at the end of the day, I got a mole fraction of the sulfuric acid equal to 0.1218. It is unitless. The other thing I want to remind you of, because you probably will be doing just a lot of this work in the calculator because the sig fig thing is so tedious, get a big set of parentheses on the denominator so that it knows that you want to add them up before you divide. So for part C, we're asked to calculate the molality. It's not too bad at this point because we've already done most of the work. So molality will be moles of solute, so in this case our sulfuric acid, divided by the kilograms of solvent, which in this case we're assuming that they used water. I'm going to grab the sulfuric acid mole value from a previous calculation. And then I have the grams of water. I'm just going to divide that by 1,000. So it's kilograms. And when I did that, I got 7.69 molal sulfuric acid. After that, we are asked to calculate the molarity. Molarity is moles over liters. So moles of solute over liters of solution. This is gonna seem so simple, it's almost too simple. The first thing we did in the problem was we assumed a liter, and that corresponded to 571.6 grams, which then we got the mole value. But we assumed 1 liter. So that's what goes on the bottom. At the end of the day, if we're going 4 sig figs, I would report my molarity as 5.827 molar sulfuric acid. So this last problem is really deceptive. It looks like it should be a quick one. It's not. They do give us enough information, but we're going to have to work really hard to extract the pieces that we need from the given information. So first off, they told us that we have 14.8 molar aqueous ammonia. Because molarity or concentration in general is independent of volume, I can make an assumption about the volume. So I'm going to assume that I have 1 liter of this solution. With the assumption of 1 liter, I now know that I have 14.8 moles of ammonia. 14.8 moles divided by 1 liter would give me 14.8 molar. That's good because when I'm solving for mole fraction, I need this value in both the numerator and the denominator. I also need information about the solvent. Because of this AQ here, I know that water is my solvent. It'd be really nice if I had the mass of water. However, I do have the density of the solution. So this value right here is the density of the solution. And I made an assumption about the amount of solution. So I'm going to combine my assumption about the volume of solution with the density of the solution to get the mass of the solution. So let me set that up. So I have 1,000 milliliters of solution, or 1 liter, and we're told that it has 0.8980 grams per 1 mil. So therefore, I have 898.0 grams of solution. Alrighty, that's something, right? What else do we know? So we know that the grams of NH3 are solute, plus the grams of the water, or solvent, should equal the grams of the solution. I have the grams of solution, and in a way I have the grams of ammonia, right? I know how many moles of ammonia I have, and I can calculate the molar mass of ammonia. And from that, I can determine that I have 252.192 grams of ammonia. So working with this, I'm going to plug in 252.192 for the ammonia. I still need to do a little bit more work to get the grams of water, and I know my solution is 898.0 grams. So I'll subtract over, and then I get a mass of water equal to 645.808 grams. Where to go from there? So that's grams of water. And this is a mole fraction problem. So I'm going to take those grams of water and convert them to moles of water using molar mass. So with that, I get 35.83840,178 moles of water. Now I'm finally there where I can start actually plugging stuff into the mole fraction equation. So for that, I need the moles of ammonia in the numerator. So 14.8 moles of ammonia. And then the total moles in the denominator. So the 14.8 moles of ammonia plus this 35.83840,178 value. Moles cancel with moles. And at the end of the day, the mole fraction of the ammonia is equal to 0.292. It's unitless.